Good morning or good afternoon, depending on where you are at. My name is Atarot Azizi Namini. I'm director of the IBT/ABC-UTC at Florida International University. Very warm welcome to more than 1,000 sites that they have registered to listen to our June 2025 monthly webinar. Today, we are bringing to you a very interesting topic, which is related to preservation of a historic bridge using an arc spray zinc anode cathodic protection. We are delighted to have with us Ray Buttenberg, who is a state bridge engineer with Oregon Department of Transportation, and David Whittemore, who is the president and chief innovation officer at Vector Corrosion Technologies. During the registration process, we have received a number of questions. Time permitted, we're going to try to answer them. If not, we will post the answer on our website. This webinar will finish no later than 20 minutes after the hour. But during the presentation, if you have some additional question, please by all means post it on the dashboard, and Paul Lyles and Rick, who are going to be moderating the question and answer period, will address them. Before I turn the screen and mic to our speakers, myself and Cathy Kroll, we would like to share some bridge-related news with you. First and foremost, I would like to brief you on our next conference, next IBT/ABC-UTC conference. The next conference, which is 2026 World Bridge Engineering Conference, is going to be held December 1st and 2nd, 2026 at Hyatt Regency Hotel in Miami, Florida. The conference is sponsored by U.S. Department of Transportation through IBT/ABC-UTC. We are also very thankful to 32 states that you see their name on the screen, 32 state DOT who have co-sponsored the conference. If you don't see your name in there and you would like to be one of the co-sponsors, please send me an email. It should be easy to find my email address, and later on it's in the slides. Also, now you can submit the abstract. Please, we hope that you plan to attend the conference. The deadline to submit the abstract is February 20. There are QR codes. Later on in the presentation, I will put these slides back again. You can go ahead and use those QR codes to submit abstract. We also have an opportunity to exhibit. And very soon, we are also going to give you a link to reserve your hotel room at a special conference rate. December and Miami is a good combination. As you might expect, the rooms are at the premium. That's why we have a block of room at a special conference rate. So we hope that you plan and you attend the conference. At this point, I'm going to turn it to Cathy Kroll, who's going to share with you some additional news related to the bridge engineering. Cathy, it's all yours.
Thank you, Torad. I'm Cathy Kroll. I'm the co-director of technology transfer at the IBT/ABC-UTC. Thank you for joining us today for our 171st webinar in our monthly webinar series. I'd like to share a few announcements with you before we jump into the webinar. I'll start with a few announcements from our industry partners. First, the Engineers Society of Western Pennsylvania is presenting the International Bridge Conference, the IBC, in Pittsburgh from July 14th through the 16th. See the link for further information. Looking a little further out, PCI, the Precast Prestressed Concrete Institute, will be hosting the 2025 PCI Committee Days Conference from September 16th through the 20th in Chicago, Illinois. If you could advance the slide, please. Registration is open for the PCI Committee Days. Next, the AISC NSBA will be sponsoring Steel Days 2025. This is a nationwide event to be held October 20th through the 24th that offers steel enthusiasts, both young and not so young, opportunities to learn about careers in the steel industry. Next, ASBE, the American Segmental Bridge Institute, will be holding their 37th annual convention in Bellevue, Washington, October 27th through the 29th. See the link on the screen for additional information. Those of you who are with us in May might remember that we announced the AASHTO Committee on Bridges and Structures annual conference. This was held in Dallas from June 4th through the 5th. Usually we announce upcoming events, but in this case, we want to share some things we learned at the conference. To keep it brief, we'll share one a month, although there were lots that we were able to learn about there. First, I'd like you to see on the screen a link to the pooled fund. So this is the Bridge Deck Preservation tool. It's a valuable resource. And it is a result of pooled fund. I didn't put this on the slide, but it's TPF5 474. It was a pooled fund that was led by Iowa DOT with participation from FHWA, as well as Indiana, Iowa, Minnesota, Missouri, New Mexico, and Texas. This is a project level tool for comparing options for bridge deck preservation of a specific bridge that is a candidate for preservation. The tool can optimize for life cycle cost or for service life extension. The tool is hosted on FHWA's InfoBridge website, which allows it to harness the data collected by bridge owners in accordance with FHWA's National Bridge Inspection Standards. So the first link on the screen is actually the link to the tool on the InfoBridge site. The screenshot, and I apologize for it being very small, but the screenshot is actually a result that is achieved by using that InfoBridge link. From the InfoBridge site, you provide some parameters and the tool will provide suggested actions. The tool gives suggestions with cost comparisons. The cost in the system can be modified to align with your state, or you can just use the costs that are in the system to get an idea of relative costs of various actions. This is a really valuable tool. Big kudos to AASHTO and the pooled fund and to Iowa for leading the pooled fund and those members for making this happen. It's really a great tool. So please do look at the links on the screen. For more information, you can contact Kyle Clute at Iowa DOT. That is all for those announcements. Now for a few of our own IBT ABC UTC events. The next monthly webinar will be Thursday, July 17th from 1 to 2:15 Eastern. The featured presentation will be on Alaska DOT's innovative use of drone technology, using everyday tools and also as emergency readiness. Leslie Dougherty, Jesse Escamilla, and Ryan Marlowe from Alaska will be presenting on how Alaska is using this innovative technology across their bridge program. Please mark your calendars and join us for that innovative presentation. Our next quarterly research seminar is scheduled for July 25th from 1 to 2:15 Eastern. It's development of low carbon concrete materials infused with biochar for bridge applications. This seminar will be presented by our partners at Texas A&M. Last announcement is regarding our annual in-depth web training. As many of you know, each year our advisory committee selects a topic to provide more detailed coverage. Our topic for 2025 is Simple for Dead Load, Continuous for Live Load Steel Bridge Systems. So you could advance the slide, please. We'll be learning about the history of the topic and how to design the system. We'll be presented with case studies by both Missouri and Nebraska, and we'll hear from our construction industry partners about fabrication and constructability. Again, this is Tuesday, September 9th. It is a 4-hour session, so please mark your calendars and join us for that. Registration actually is already open for that event, so please do go to the website and register. All right, that is the last of our announcements, but before we dive into our featured presentation, I'll go through a few housekeeping items. As many of you know, these webinars are recorded and posted to the IBT ABC UTC website in the section titled Monthly Webinar Archives. So you can access this and all previous webinars for future learning and to share with interested colleagues. I'd also like to point out that a PDF version of today's presentation is provided in the GoTo dashboard on the right side of your screen. You can download these PDFs during the training session. They will also be posted in the archives. Lastly, this presentation will be followed by approximately 15 minutes of question and answer. Please enter any questions you have in the question box in the GoTo dashboard. With that, we will begin our featured presentation. I invite the presenters to turn their webcams on for introductions. It is with pleasure that we welcome Ray Bottenberg, the Oregon State Bridge Engineer, who is well versed in this topic by way of his significant involvement in the development of AASHTO's Historic Bridge Preservation Guide. Thanks to Ray for his efforts on that. And also Dave Whitmore, President and Chief Innovation Officer with Vector Corrosion Technologies Ltd. Dave is an industry expert and frequent contributor to our webinar series. We welcome you both, and I will now turn the screen controls over to Ray.
Thank you, and appreciate the introductions. The bridge in the introductory slide here is Yaquina Bay Bridge in Newport, one of my very most personal favorites, and one that we're going to talk about a great deal in the next half hour or so. Just a quick outline of where we're going here. I'm going to share the location for those that aren't familiar with our area so much. I'm going to discuss briefly the history of Conde McCullough, the designer
Ray,
of...
I don't know if you can hear me, but I am not seeing the screen. I'm seeing the GoTo webinar page.
Ooh, I actually am seeing the screen.
Now it's on.
Okay, very good.
Okay, very good.
Okay.
I've seen the title slide. Thank you.
So we're on track. Okay, I will talk about the history of a certain group of 5 coastal bridges that represent McCullough's pinnacle of his career. We're going to talk about corrosion and some specifics on Yaquina Bay Bridge and what's been done to protect it, and a little bit of details on ODOT's Cathodic protection and repair program, and then we will close and have questions and answers. So the location, so on the left we see a map of the United States and Oregon highlighted. On the right we have a view of our coastline, and so the bridges that you see here all were designed by or under the direction of Conde McCullough.
You're not seeing, are you advancing the slides?
So you should be seeing location with 2 maps.
I am noticing that there is a little bit of a delay today, so I'm just letting everyone who's watching, I apologize if the slides are a little bit behind the speaker, and speakers, if you could maybe advance a little bit ahead of time. It does seem like we've got a little bit of a delay. But Ray, I do see the location Oregon coast, so we're good to go.
Awesome. I will try and be a little bit ahead on switching those then. So the 5 bridges of particular interest are number 6, Yaquina Bay Bridge, one that's not shown here because it was demolished at the town of Waldport, Alsea Bay Bridge, Siuslaw River Bridge in Florence, Umpqua River Bridge in Reedsport, and Coos Bay Bridge in Coos Bay. And so, do we have the slide for Conde McCullough?
Yes.
Okay, so I need to talk a little bit about him and his career. So he was born in 1887 in Redfield, South Dakota, and was actually an only child in a time when that was a very rare thing. He attended Iowa State College, civil engineering. A gentleman named Anston Marston was the dean and probably his primary instructor. After graduation, he worked for the state of Iowa. He worked for Marsh Engineering Company designing bridges for the state of Iowa. Marsh was an expert in reinforced concrete arches, and McCullough learned a great deal from him. They focused on through arches, much like the one on the left here, and also bowstring or tied arches. And that education got carried forward spectacularly. He went to work for the Iowa State Highway Commission, Highway Department in 1911, and a couple things were happening there that were pretty pivotal. There was a thing called the Good Roads Movement, which probably hit most states during that decade. And there was also a pretty pervasive thing where bridge companies were traveling the country selling bridges to county commissions, bridges that maybe didn't match the need of the site, maybe that were overpriced, and various issues that cost a lot of money and didn't serve the need. And so while at Iowa State Highway Department, he focused on standard designs, and also notably he focused on matching the bridge to the needs of the location. So after Iowa Highway Department, he was recruited to be a professor or assistant professor at the Oregon Agricultural College, which is now Oregon State. The civil engineering department had a staff of 4, and he was the only structural engineering professor. In 1919, he was tapped to be the state bridge engineer at the Oregon State Highway Department. And in the process, he took all but one of his graduates with him. And I think at least 2 of them became state bridge engineers later in their careers after McCullough himself. And so during that period, he basically contributed to building out the highway system for the state of Oregon. And so literally hundreds of bridges throughout the state were designed under his direction, and really did a good job filling out that highway system. And actually dozens and dozens of them survive today. In 1935 through 1937, he actually took a sabbatical, you might say, and worked for, I believe, Bureau of Public Roads to design 4 suspension bridges in Central America, in countries of Panama, Honduras, and Guatemala. And and you see 1946 is the end of this timeline. Actually, he, I believe, was still employed with the State Highway Department when he passed away in 46. And the slide for his later career should be showing here soon. Basically, really the high point of that career, in my opinion, was construction of 5 major bridges on our highway on the coast. They crossed 5 different bays and major rivers, which all had ferry service up until 1936. They took advantage of PWA funding or actually a loan to build these 5 bridges. And in order to meet the terms to get the money allocated, they worked 2 shifts during 1933, and in a 6-month period designed all 5 bridges. And they were built simultaneously between 1934 and 36 also, which either fact is impressive, so the design and the construction. And on the left is a picture of the Coos Bay Bridge being constructed. In the middle is a picture, I think, dating to the Central American years. And then on the right is a picture at another bridge that he designed in Gold Beach, Oregon. And so a little bit about the PWA projects, the 5 bridges. Again, it eliminated 5 ferries. The locations were Newport, Waldport, Florence, Reedsport, and North Bend. McCullough is widely quoted. The wording varies from quote to quote, but the quote is, the bridges are jeweled clasps along a matched string of pearls, where the pearls are the sections of the coastline between the bridges. And at left, you see the very north portion of the Newport Bridge at Quina Bay. And then on the right is some iron workers about the time that the main arch was being closed. So I'm going to just go through each of those 5 bridges briefly here. This first one I'm going to discuss is Alsea Bay Bridge, which is 3,000 feet long, or excuse me, the original one was 3,000 feet long. The picture here is an art rendition that was done before construction. Really beautiful bridge. Concrete deck arches match up to symmetric tide arches that cover the navigation channel. This particular site didn't have a great deal of navigation relative to the others. The bridge was constructed between June of 34 and May of 1936, cost of about $750,000. The estimate was just a little higher than that at around $780,000. So in the town of Florence, we have Siuslaw River Bridge. Here's the art sketch of that bridge before construction. This one has tide arches and then a double leaf bascule span over the navigation channel. And it was constructed between September of 1934 and June of 1936 at a cost of $500,000. And it is noted as a known fact that there were no fatalities in its construction, which is remarkable and good. So that proceeding down the coast in Reedsport, we have Umpqua River Bridge. This one has concrete tide arches, and they match into a movable swing span that covers the navigation channel. The movable span is 430 feet, so you've got about 200-foot navigation channel on each side of the draw rest. And here's construction of that bridge in Reedsport. If you look closely, you can see that the movable span is partly painted and partly not at that point, which probably caused some issues later. It's built from October of 1934 to August of 1936. Cost about $550,000, and there were at least 3 fatalities on this bridge. The biggest one is in the town of North Bend at Coos Bay, and this one's a mile long. And basically, we have concrete deck arches tapering up larger and larger up to a cantilever truss that's unusual in how smooth it looks for a cantilever truss. It's matched in with those arches pretty well. Coos Bay Bridge during construction. The photo here shows, actually it's a Japanese trainer that passed through during construction. It would not have fit after construction. The bridge has about 145 feet of navigational clearance. It was built August 1934 through June of 36. It cost $2.1 million, and there were 2 fatalities on it. A little bit of highlight on some of the aesthetic treatments. These bridges got a little bit of decorative treatment to for the public good. And so you have graceful lines and a lot of Art Deco style detailing, more than just what's shown here. And it is pretty. And finally, this is at actually the north end of the group of 5 bridges, but Yaquina Bay Bridge at Newport, 3,200 feet long. This is the art view of it. This one we have concrete deck arches from the south approach leading up to larger steel deck arches, which lead to a 600-foot steel arch. And the approaches are not symmetric because the north end is on a bluff, so it's higher than the south end. So construction on Yaquina Bay Bridge went from October 1934 through November of 1936. The cost was 1.26 million, and there were at least 2 fatalities. The cost estimate was 1.38 million, and I should point out that there was tremendous pressure to bring these in under estimate, basically, because of the times and the source of funding. So fast forward 50, 80, 90 years ahead, and you'll see a lot of things like these 2 photos. These bridges are all really close to the beach, and what you get is salt in fog, salt in wind, all pretty constant attack, and the salt basically sets up a situation where the reinforced concrete has a ready electrolyte by way of the salt, and on top of that, the salt is a catalyst also for the corrosion, and the rebar corrodes and then spalls the concrete off, and then it turns into a spiral of badness. So that effect led to what you see here. So during the decade of the 1980s, the Alsea Bay Bridge in particular started to show its age, and it's had a lot of spalling concrete issues. There were periods when ODOT tried to basically prevent boats from being under the bridge to keep falling things from hitting them. They went through a period of trying to scale the bridge on a regular cycle. Nothing was really satisfactory, and so they determined that they needed to replace the bridge. So, and it was replaced. You can see in the photo the new bridge to the left of the old bridge as it's being demolished. That bridge, the new bridge, cost $41 or $2 million. A lot more than the old one had. And the community was very unhappy. They liked their McCullough Bridge a lot. And so ODOT started their bridge preservation engineering unit basically to go and find the technology to start applying impressed current cathodic protection, basically to save the other 4 of those bridges and others. So one of the key elements of that technology was the arc sprayed zinc. There was some research done in California by Caltrans with zinc arc sprayed, and what we found there was a metal with excellent anode properties that is gray, and so you put it on your concrete, it doesn't look that out of place. And so in 1991, at the same time as we were demolishing the old Alsea Bay Bridge, we put cathodic protection on the Cape Creek Bridge. That was after concrete repairs were done, and you see the results on the lower center picture. The upper left picture is the arc spray application, and Dave will cover that more. And I believe we're at the point of switching control.
Okay, so just to follow on from what Ray was talking about, in 1991 they did that project that he just showed, and then in 1992 they did the initial application of arc sprayed zinc.
Could you put in presentation mode, please?
Okay, it should be.
I actually do see the presentation mode, so I apologize to the people on the line. It sounds like people are having different experiences. So I hope everyone or most people are seeing what I'm seeing, but I am seeing the correct slide.
Ray, do you see presentation mode?
Yeah.
Yeah. Okay. Okay. So okay, hopefully most other people do as well then. So the next bridge that was done, the first big bridge that was done as part of this program was on the Yaquina Bay Bridge. It's one of 11 bridges that were designed by McCullough along the Oregon coast. It's a little over 3,000 feet long, has over 30,000 cubic yards of concrete in it, and a little over 300,000 square feet of metallized zinc impressed current cathodic protection was applied in 1992. And at the time, it was, I think, the largest substructure project ever undertaken. And even today, it's certainly one of the top 5 or 10. And then over the years, we'll see how it served a useful life, but it was removed and reapplied in 2020. And Oregon DOT learned a lot over all these years, and one of the things that they learned is that they used performance-based pre-qualification, which is really helpful for quality control. And so in 2020, and I'm not sure how fast you see these pictures come up, but this is a picture of the bridge in 2020. You can see on the right-hand side some places where the zinc that was previously installed is kind of bubbling or debonding. And a couple of more close-up pictures here on slide 23 shows the condition of the zinc after almost 30 years, 28 years after the original installation. And you can see in some places the zinc is flaking off or blistering and debonding. And that is happening because the zinc is being consumed by the cathodic protection process as the system is working. So eventually you don't have metallic zinc on the surface, and the system will cease to work. So what are we talking about here when we talk about arc sprayed zinc or metallized zinc? We are basically taking pure zinc in the wire form. We're melting it, and if I can turn on my pointer, laser pointer, we're melting those wires together in an electric arc, and we're blowing that molten zinc onto the prepared concrete surface using compressed air. And that is basically the process that's used for putting the zinc onto the concrete surface. And so basically we're applying a thin layer of metallic zinc onto the prepared concrete surface. Normally this is done with pure zinc, but in some cases aluminum, not very often aluminum by itself, but aluminum zinc alloys are sometimes used as well. And there's lots of different names for this process: arc spraying, electric arc spraying, metallization, thermal metal spraying, etc. But it's all the same process. And I'm going to walk through the steps in the application, everything from mobilization all the way through to quality control and installation of the rectifiers. And so I have slides on each one of these steps. So the first step in the installation process is to have a proper environment to do the work, to get access to the work area and to have a proper environment. And so in this photograph, you see a work enclosure installed for one section of the bridge, and fixed frame scaffolding for access, and that's in behind the work enclosure as well. And the sections to the right are completed with the reapplication, and they're working in this direction to the left. The access shown on the right that was used on this particular job was generally fixed frame scaffolding, so that you had access to every square foot of the substructure of the bridge, and that fixed frame scaffolding was closed inside of an environmental enclosure, because to get proper quality control and proper bond of the zinc, you want to make sure that the environment in there is managed, particularly in relation to moisture. There was very little concrete damage that had occurred over the 28 years that the system had been running, but there were some concrete repairs that were required, and those concrete repairs were done using traditional concrete repair materials and traditional concrete repair techniques, the same as would be recommended by International Concrete Repair Institute, or ACI, and covered in some of the various AASHTO specs as well. So concrete removal and replacement where the concrete is delaminated or no longer functional. And on the right-hand side here, some crack injection, which was done by epoxy crack injection on the right. One of the things that you need if you're going to do cathodic protection is that you need to have electrical connections to the reinforcing steel. So the picture on the left shows an electrical connector that's installed on the surface of the concrete, but this brass pin goes all the way.
May I
Yes.
interrupt?
Of course.
I'm gonna give you the screen control again. Okay, that may solve the delay. If you don't mind, just give me a minute.
I'll exit out. Okay, not a problem. Okay, so on the left-hand photograph here, you see one of the electrical connections that's installed on the surface of the concrete, but this brass pin actually goes back into the concrete to connect to the reinforcing steel. This allows you to electrically connect to the reinforcing steel from the surface of the concrete. Those are put in on a spaced basis as required in the specification. And the other thing that you need to have installed in the concrete are, these are sensors. We call them reference electrodes or reference cells. They are embedded inside the concrete and they allow you to measure the potential or the voltage of the reinforcing steel while the system is running, and that's a way that you can verify the performance. So in terms of the zinc related aspect of the work, the picture on the left shows the condition of the zinc in 2020. So this is the 28-year-old system on the left. That zinc is removed, and then a new layer of zinc is applied to the concrete surface on the right. The removal was done by abrasive blasting, essentially a light, as light as possible sandblasting to remove the existing zinc without damaging the concrete surface as much as possible. And then once the surface is prepared, the zinc is sprayed onto the surface, and hopefully you're going to be able to see this little video showing arc spray being sprayed. Now, when we did the trial before this webinar, for some reason the audio is not hearing there, but it's like spray painting, but it's a very loud kind of combination between blowing with compressed air and a small engine kind of running sound. It's a little bit of a noisy process, and you should definitely wear hearing protection. So hopefully you could see that spray application. Quality control is really important in these projects. On the left, one of the things that what's being measured on the left is the temperature of the concrete surface. You're going to want to measure the temperature of the concrete surface as well as the humidity. That's important to make sure that you're well above the dew point, because you're spraying hot zinc onto this concrete, onto the surface. So if there's moisture there, it's going to vaporize and it's going to give you problems with the bond. On the right, one of the other things that will be specified is to measure the thickness of the zinc, and that will include removing some sections and physically measuring the zinc and then touching up those areas. And probably the most important quality control thing that is going to be specified is to measure the bond of the zinc to the concrete surface. And so on the left, we have basically a pull-off test device. On the right, you can see the pull-off test device after the pull-off is complete. You can see the layer of zinc on the dolly, and you've pulled the zinc off of the surface of the concrete, and you're going to measure the pull-off strength in PSI. Normally, most specifications are going to say around 150 PSI or greater, or something in that range. That's 278. This is from another test, 268. So both of those are good. And then once the zinc is installed and you're ready to, start using the new system, you need to connect the zinc and the reinforcing steel back to a DC, direct current power supply. We call that a rectifier. So this unit on the right is taking AC power, regular 110 volt. You can get them wired for 220 volt if you want, but 110 volt AC power, and converting it to variable voltage, low voltage output DC power. And the unit is broken down into zones. So each zone is going to have wires running out to a section, and that section is, each section of the bridge is going to be controllable. So that's something that's important and necessary for the impressed current aspect of the work. Here you've got a picture on the left of the condition of the bridge before this work that was done in 2020. And on the right, you can see the same area after the previous zinc coating's been removed and the new zinc coating has been applied. So it looks fairly nice and uniform. And here you can see a couple of photos of the piers after the reapplication, and you can see there's a kind of a gray, essentially a grayish color to the applied zinc coating. Oregon DOT and Vector were both very fortunate. This project was nominated and won a Concrete Repair Award of Excellence at the ISRI Concrete Project Awards in the fall of 2024. So that's really good, and everyone is happy about that. And so what's the value of doing this? I mean, basically you're taking a unique and historic bridge, and you're maintaining the bridge and its aesthetic. We're not adding any dead load to the structure. We're providing global cathodic protection, global corrosion protection to protect the entire substructure of this historic bridge. And the rehabilitation and service life extension, the total cost for this project was roughly 10% of the estimated replacement cost for the bridge. Now, other DOTs, many other DOTs are using arc sprayed zinc or arc sprayed aluminum alloys in different ways. As Ray mentioned, California did the original work with impressed current. Oregon has done by far the most with impressed current arc sprayed zinc. A few other locations have done some as well. A lot of states are using arc sprayed zinc and using it galvanically, which is simpler to install and less upfront cost, but it doesn't have some of the advantages that the impressed current option does provide. In terms of lessons learned, surface preparation is really important, and in terms of QC, surface preparation and making sure that the surface is dry enough, the application environment is dry enough, are probably two of the most important things. If the zinc is installed properly, it's very durable. This system lasted between 25 and 30 years, and Ray may comment on this later, but he and I share the view that if they ran the system a little bit differently than they did, it will last well over 30 years. And just to follow up from the last slide, impressed current systems are more complicated than galvanic systems, and then they do require a permanent power supply. but they have the advantage that they can be adjusted to compensate for the environmental conditions as required over the service life of the system, which is a big advantage. Obviously, there's other ways that you could protect the structures, and just want to show you that, although arc sprayed zinc impressed current was chosen on this particular project, there are other options out there. And depending on your situation, you might choose arc sprayed zinc, or you might choose one of the others. One option is carbon-based or graphite-based conductive coatings, which Oregon has done on a few structures. This is one bridge along the Oregon coast that Oregon DOT used conductive carbon anode on the surface. And so this area that's kind of the darker gray from the deck down, that's the area that's protected with the conductive coating, carbon or graphite-based conductive coating impressed current system. That's one option. Another option that can be used if you have carbonation problems is realkalization. And again, an Oregon example on that. This is a bridge not on the coast, but close to the coast, historic concrete arch bridge that was suffering because of carbonation-induced corrosion. And Oregon DOT used realkalization. It's essentially a system that is temporarily installed. It's an impressed current system that is temporarily installed and then removed from the structure to protect it. And then you can see it's been protected, or has a nice light whitish colored coating applied, so it looks really good afterwards. And a third option that's used by a number of DOTs for both historic and non-historic bridges is electrochemical chloride extraction. Again, this is an impressed current system that is temporarily installed on the structure for the purpose of electrically drawing the chlorides out of the concrete and increasing the pH of the concrete, basically to repassivate the steel. And Caltrans has been using this approach on a number of their coastal bridges, including the Big Creek Bridge, which was done in the same year as the Akina Bay zinc spray reapplication. So with that, I'm going to turn the talking here back over to Ray, just to talk a little bit about the value of doing this work and close out the seminar.
Yeah, thank you, David. So I'm just going to talk about a few things about the value and what we get for it, and sort of the program aspect. But of course, we get historic preservation, which complies with state and federal laws. There's aesthetic value. That Dry Canyon Creek Bridge on the left is in the Columbia River Gorge scenic area, and it turned out really beautiful. A lot of times the projects will have reduced traffic impacts compared to other alternatives, and reduced environmental impacts compared to other alternatives. And typically they can be good stewardship of public funds. One cathodic protection project that we did in the last decade changed a $30 million bridge replacement that would have had a 100-year design life into a $3.6 million rehab project with a 20-year life. And if you annualize those cost figures, you're sitting at 1.2 million per year to replace the bridge, and 265,000 per year to rehab it. And so that's a pretty strong incentive when it's the right thing to do. As far as the program, I'm not going to belabor what this list is. It's most of the McCullough bridges and some others on the coast that are close to the beach. There are 14 independent bridges on this list, and so that's the size of our program. And this one repeats a little bit from 2 slides ago, but some of it doesn't overlap. Again, historic and aesthetic values, cost savings. Some of the bridges that we're doing cathodic protection on are not historic, and we're just doing it because it's the right thing to do from a cost standpoint. Again, reduction in traffic impacts, community impacts, the right action at the right time. So that bridge that I shared cost figures on 2 slides ago is in an area where someday maybe it'll need 4 lanes, but that's a long ways out. And you have, if you replaced it, you have to choose whether to build a 2-lane bridge or a 4-lane bridge. By doing the cathodic protection, you put off that decision until it's closer to being relevant and appropriate. And then lastly, there are environmental benefits. Reduce, reuse, recycle applies to bridges too. If you can reuse it, that's better than doing something else. And on the right is not a McCullough Bridge, but it's St. John's Suspension Bridge in Portland. That's a David Steinman design from 1931 or 2. We're pretty proud of it, and our preservation unit has been deeply involved in keeping it. So I think we need to move to the next slide at this point.
Yeah.
And so thank
With
you.
that,
yeah.
Despite the delay in the slides, I thank everyone for attending the webinar, and hopefully they were able to follow along. And thank you, Ray, for doing this together with me.
Okay. Thank you, Dave. Thank you, Ray. So at this point, we're going to turn it to Paul and Rick to moderate the question and answer period. Paul?
Okay. Y'all hear me all right?
Yes.
And, go ahead, and David and Ray, let's get our cameras on and we'll get into the questions. We've got a bunch of questions coming in, and there's a whole lot more coming in, so we'll go ahead and get on them. First one I have is some questions that came in pre-webinar. And the first one is, what factors affect the quality of the application, adhesion, and long-term performance of the coating? You mentioned specifically temperature and humidity. Is there anything else, and what time of year did you do these? Was it in the summertime?
Well, I would say moisture is probably the biggest thing you have to be careful about, because if you have any free moisture on the concrete surface or in that surface layer of the concrete, because you're spraying hot material onto the surface, you're going to create steam, and that's going to create a poor bond. So making sure that you're well below the dew point is key, and making sure that the concrete surface, like if you're doing concrete repairs, that you've left them long enough that they've dried out sufficiently, etc., those kind of things. And I'd say the other thing is you want to have enough roughness from the surface profile. And I'm not sure if that sound is coming from me or...
I think it's Paul. Paul, a little bit, put the mic.
Maybe it's me, but the other thing is that you want to have the surface rough enough that you get a good bond, but you don't want to blast it so hard as to remove all of the cement paste, because you're passing the current through the cement paste, so you want to leave as much of the cement paste on the surface as you can.
Okay. What time of year did you do it? Was it the summertime?
We try to like that, but with the work enclosure, we were able to work through most of the good part, almost all year round out in Oregon.
Okay.
Yeah.
Were the chlorides tested to verify this was the correct treatment for the application?
For the population of bridges that we are doing cathodic protection on, yes, they were tested, but it wasn't really necessary. They're so contaminated. In fact, actually, so that bridge that I gave the cost data on was the second most contaminated one in our database.
Okay. Question about what are the recommended welding processes for repairing old steel with low weldability, maybe?
Ooh, I'll leave that to
So-
Ray because that
Well,
that's not related
so
to
the-
today's topic.
The bottom line is to treat it as if it's a super high carbon content steel, and so there's lots of preheat and all the extra care that you have to do with the high carbon.
Okay, what is the frequency of monitoring after installing this type of system?
Well, I could say, if you go according to code, you're going to want to monitor it fairly frequently when you first install it, typically monthly, maybe, and sliding to quarterly, maybe in the second half of the first year. And then after that, you're going to want to monitor it, if possible, a couple of times a year. Now, that may not be possible in all cases, and Ray can talk about the practical experience as the owner, but that would be the recommended monitoring program. And if possible, now today, almost all these jobs today have remote monitoring installed, which was not the case on the stuff that was installed 20, 30 years ago.
Right. Historically, we've dabbled with remote monitoring most of the last 30 years, and that's super important. And then you back that up with some site visits on a certain number of months recurrence to
Okay.
back it up.
Okay. The Aquina Bay Bridge has concrete and steel arches. Are the steel arches also protected from corrosion with arc spray zinc, or are they just painted?
So they are not protected by arc sprayed zinc. They are painted using a 3-coat moisture cured urethane system with a zinc primer.
Okay. Is that the same thing with the other steel in Coos Bay and
Yes.
Siuslaw? Okay.
Yeah, that's a system that we really like on our coastal bridges.
Do they? Do you do the zinking painting, and how often do you have to paint the paint, I guess?
Actually, that's about a 15 to 20 year cycle on the worst coastal bridges.
Okay. All right. Question beforehand, how many years do you expect to get out of the rehab of the bridge? You were saying 25, 30. Then when you did the first coating, did you expect them to be this long, or was it pretty well come in what you expected?
So the calculation, I believe, was for 20 years.
Okay. Okay.
Yeah, and they got 28. They got 28 out of this one, and I think, it's been run probably a little harder than it needed to be run at certain times over this period. So I think if you were, running it not so hard, you could certainly you get over 30. Anyway, how much over 30 it might be a debate, but you might get to 40.
Yeah, and that's a hindsight thing. The folks back when they set it up were doing what they thought best and
Yeah,
did a good
sure.
job. But looking back, I think we could have done something different.
Okay. How often are these bridges inspected, and are the inspectors required to have special skills?
Well, so the basic inspections, when you think about bridge inspection, that's every 2 years. And those inspectors, they're not specialists in cathodic protection typically. And so we're having them, ideally, they're communicating with the cathodic protection folks.
Okay, a person said he was familiar with vector corrosion zinc anodes that tied directly to the rebar. Please explain how the arc spray is different. And we're going to refer back to our earlier webinar that we had back in October of 2024 for people that want to see that webinar. Go ahead.
Yeah, okay. So, the couple of primary differences. One, the type of anodes that he's referring to are galvanic anodes. They're zinc-based anodes, and they have a chemical activator. They're electrically connected directly to the steel and embedded inside the steel, and they operate just naturally based on the voltage difference between the zinc and the steel. this type of system, you're using zinc as the anode, so it sounds the same, but here we're basically spraying a layer of zinc on the concrete surface, and we are connecting that zinc back to a DC power supply, and it's the DC power supply that's controlling the amount of current that's going to the steel. So you can use that power supply to push more current through this system than would happen galvanically in, for example, dry situations, but you can also use the power supply to slow down the current from the zinc to the steel in other situations where you might have a very wet or conductive environment. So you can basically manage the current. You basically have complete control over managing the current with this type of system, whereas a galvanic one is just going to happen. You have a voltage difference between the zinc and the steel, and the amount of current that's going to flow is going to vary depending on the environment and how wet or how conductive the environment is.
Okay. Question, then how would you prevent electrical shorts between the zinc anode and the reinforcing steel?
Okay, well, that's a key thing that's going to be in the specifications. It was here as well. And because with an impressed current system, you cannot tolerate electrical shorts between the anode and the rebar. If this was a galvanic system, then shorts are fine. So that's one difference there. And how do we manage it? We manage it basically by, we make a connection to the steel, and we have a connection to the zinc as we're spraying it. And the moment, if you see, basically you're going to see a voltage difference when the zinc is separate from the steel. And if you go over a short, like a small piece of exposed steel, and the zinc touches it, that voltage difference basically disappears. And basically we have a small unit that basically beeps, sounds an alarm, and this operator will stop spraying at that point. And then because now you know that the area where the short is right where you were spraying in the last 15 seconds.
Okay.
Yeah.
Okay. Are there any site protection containment measures that need to be taken beyond what is needed for conventional concrete repair? I think you had enclosures in there, and that looks something like a painting type enclosure.
Yeah, so we have an enclosure there for two reasons. One is basically to control the atmosphere so that it's not too wet. That's for application. But the other thing is when you're spraying the zinc, it's like welding zinc or welding galvanized. You're going to have some of that zinc basically burn as part of the process, and so that enclosure is an environmental enclosure as well to keep essentially the zinc dust or the zinc fumes from contaminating or people in the area. And the people working inside the enclosure when you're spraying zinc are wearing suitable protective equipment.
Okay.
Basically, it's specified as an SSPC Class 1A type of containment.
Okay.
Negative air pressure.
What is
air pressure?
Yeah. What is the anode throw distance with impressed current and surface anode repair? I'm not exactly sure on this one.
You'd be somewhere in the. You could throw probably up to maybe 2 feet, but in most cases, if you have some steel that's closer than that, that's where the majority of the current is going to go. So I'd say from a practical point of view, it's probably within a foot in most cases. But if you had a thick concrete section with steel further away from the surface, you could go 2 feet or possibly even a little bit more than that.
Okay. Is the long-term plan to continue repeating this treatment every 20 years or so?
Yes. And in that list of our inventory, actually there were 4 bridges that have been redone so far, out of that original 14.
Okay. Question here was about how does weather impact material used under this project? You kind of commented on that already, I think. You want to add anything to that?
So the weathering on the outside surface of the zinc is probably far surpassed by the consumption of the zinc at the interface to the concrete.
Okay. We'll look at a few others right now, and then it's a few minutes after 2. So how did the state historic people view the metallizing, and did they require mock-ups prior to acceptance of the finished appearance? And was any top coat used?
Okay, so no top coat. This predates my knowledge, actually. I am grateful that they, what I've heard was that they were pretty happy with the appearance of the zinc coating relative to concrete, and so it got a pass.
Okay. The question came in about the confidence level that it's going to last 28 years. You got a pretty good confidence levels in the sense that you've already gone through one iteration of it. So you want to comment on that at all?
Yeah, I'm not sure what to say beyond what you just said, Paul.
Okay.
Yeah, I mean, it already lasted that, and that's with more basic operation and control than what is being used today going forward. So I would say what they got would be the worst case scenario of what should be expected going forward.
Okay. Can solar be used for the DC impressed current?
Yes.
Y'all haven't tried that though, have you?
We have tried it with, we have other bridges with solar impressed current on them, but not with arc sprayed zinc as the anode. But it's just a different anode. So that would be, yes, you could do that. I don't think you have any, Ray, do you, that have solar on zinc?
No, we had one that had a wind generator, but it got vandalized. And
okay. How much has the traffic volume changed over the past, what they said 100 years? These haven't quite been here 100 years, but they're getting there.
Less horses.
Tremendously.
Okay. And then there's one more question, and I'm going to turn it over to Rick. But the question was were earthquake effects looked at all when you do the upgrades?
So each of these bridges has received a phase 1 seismic retrofit, which is the basic keep it from coming off the seats and so forth type of a retrofit. The foundations are in pretty complicated substrates, and so getting much more than that phase 1 retrofit's pretty hard to get.
Okay. I'm going to go ahead and turn it over to Rick. There were some questions here that were pretty involved and complicated, and I don't know how much time we have for those. We will give you a chance to answer some of these, and we will post those. But Rick, go ahead and let you get up the remaining questions that we have here.
Yep, thanks, Paul. We'll try to get through them here. Thanks, Ray and David. It's a great presentation. One of the questions I got here at the top of the list is how many times can arc zinc spray protection be removed and reapplied? Is it feasible every 20 years or something like that?
You know, each time you sandblast it, you take away some of that cement paste that David referred to. And so I don't think you can just keep doing it forever.
Yeah, there's a limit to it, right? So also,
it should be a few times anyway, I would expect. I mean, as far as everything I've heard, the performance of the second application is working, as expected. So yeah, I mean, that's a trade-off.
Yeah, and I believe some folks have talked about adding, you know, a new layer of cement paste to facilitate it too.
So there was a number of questions about cost, right? I mean, what's the current cost per square foot or something like that? I guess is that, I know you mentioned cost of some of these projects that were done, but is there kind of a base price right now, let's say? And maybe David can, I know it's location, stuff like that, but maybe there's a range of prices for putting this stuff on by the square.
Yeah, I think that's a dangerous thing to speculate over the phone, because there's so much there. I mean, you know, the access and the enclosures and everything else, you know, it's, yeah, I think I would highly suggest that if you are considering something like this, that you look at it on a case-specific basis to make a decision, and don't just use some rule of thumb that you heard from somebody.
Because the kind of rolls over into the long-term maintenance. Obviously, you got a system you have to maintain, and I guess, Ray, is that what's the cost? Is there? I mean, obviously there's an initial installation cost, but then there's a maintenance cost to keeping the system going.
Yeah, and it's hard to break that out because of who's doing that work. I guess in our case, I think that ongoing maintenance might represent part of an FTE.
Sure. So you guys do that in-house? I mean, do you have contracts that take care of that stuff for you?
Some of both.
Both? Yep. Okay.
Yeah.
Okay. Let's see if I can find another one here. Zinc. The zinc, is it ever covered with another system? I think there was something there was mentioned about some paint, some zinc paint or something. I guess, how common is that? Is that to get the color, or to get some?
The arc sprayed zinc is the arc sprayed zinc, and that's the color you see.
Okay.
The graphite example that David shared actually is top coated to get the color.
Yeah, because it's pure black. The graphite or carbon-based coating is pure black, so you generally have a top coat on there for aesthetics. This question may actually relate back to, in some areas like Florida, they have used over the years a lot of arc sprayed zinc, not as impressed current, but as galvanic, and in marine environments. And they very often, I think in their standard spec, they will put a top coat onto the zinc. And maybe it's partly for aesthetics, but it's primarily there because they're directly in the salt splash and spray kind of zone. It's more to prevent or self-corrosion of the zinc because of saltwater spray onto the surface of the zinc, same as you would if you had a galvanized steel elements in that environment. Okay. So they'll put a top coat on there for basically protecting the outside surface of the zinc from corroding.
One last question. As the zinc applicant, I guess, expends its life, it looked like it comes off in possibly large flakes. And is that the way it comes off? And then is that a concern as far as how that's coming off environmentally? I think one of the pictures you showed early on showed where some chunks were coming off.
Yeah, I'd say that's probably unusual. Not to criticize anything from the past, but probably it was sprayed a little bit over thick on the top of those arches there. In most places, you'll get corrosion of the zinc, and it'll be more flaking, small little flakes, and kind of,
Could be surface prep too is important, obviously, to get it.
Yeah, surface prep is also important too. Yeah, for sure.
Okay, well, with that, the great presentation, guys, and it's a great subject, and I love the historic route up and down Oregon there. I've drove it myself, and I look forward to doing it again in the future. So, but now that I got all this extra information about that area, so with that, I'll turn it back over to Adirad, and he can wrap things up. So, thank you very much, guys.
Thank you, Rick. Thank you, Paul. Thank you, Dave and Ray, for a great presentation.
Thank you.
But on that note, we are going to conclude our presentation and hope to have every one of you with our next webinar. Thank you.